Hello everyone, my name is Daniel Sando. I'm at the University of New South Wales in Sydney, and today I'm going to talk about a ferroelectric domain wall memory, which we think could be a new data storage paradigm. So it's kind of no mystery, I think, to the audience here that computing for humanity is reaching some fundamental limits. We hear things like the end of Moore's law and things like this, where we need new paradigms to use less energy in computing, to be able to move things around faster and more efficiently. And so in one of the ways to do this is to find new memory, new ways to store information. And so we think that this device is one possible avenue. So let me just move my screen. Yep, so here we go. We have a ferroelectric material. So it's a ferroelectric domain wall memory. And I'll introduce very quickly what is a ferroelectric, because I think some of you may not know ferroelectrics very well. So essentially a ferroelectric material is a material that has a spontaneous polarization that we can switch with an electric field. Now you may be familiar with a loop that looks like this. This is a hysteresis loop. And you may have seen this for a ferromagnetic material where you have the magnetization and the applied magnetic field here. But for a ferroelectric, it's very similar. Instead, we have a polarization and an applied electric field. Now, the two stable states that we have at zero field in this material allow us to make a memory device. And of course, this is the basis for magnetic hard disk drives, for example, in ferromagnets. And in ferroelectrics, we've also made things called ferroelectric random access memories, which work on the same process. Now, something that's very interesting about ferroelectrics and ferroic materials generally is that they form domains. When we create the crystal, when we make our sample, we have domains of different directions of polarization. So for example, here we have a polarization down and here we have a polarization up. And necessarily between these different domains, we have what's called a domain wall, which is the boundary between these two domains. Now, an interesting thing about these domain walls is that some of them can actually be conductive. So in this material, bismuth ferrite, which is I'm going to call BFO from now on, if you create domain walls in this material where you have polarization directions that are going in different directions, at some of these boundaries, if you measure the electrical conductivity of your material, you actually see some hot spots here. And so essentially this material is actually an insulator, but at these domain walls, you have higher levels of conductivity. And so this begs the question, this was discovered about a decade ago roughly, and it begs the question, if you can create these domain walls in these materials, can you create essentially circuitry that you could modify at will? So if you could make agile circuitry where you could write some circuits and then erase them later to reconfigure your device. And so this is essentially what we're trying to do with our domain wall memory here. One thing that I'd like to highlight before moving on is that ferroelectric domain walls have some benefits compared with ferromagnetic materials in that they're actually very small. So they're of the order of 1 to 5 nanometers in size, which is an order of magnitude smaller than ferromagnets. And as I mentioned before, we can use electric field to actually write these, erase them, and move them around as well. So it allows us to make this agile circuitry a reality. Okay, so let's have a look at what we've been doing in our group to kind of use these domain walls in a functional memory device. So first of all, we need to, of course, fabricate our samples. So the samples that I'll focus on here are bismuth ferrite, BFO, grown on strontium titanate substrates around 50 nanometers in thickness. These are grown by pulse laser deposition, a fairly common technique in our field. We then go to ANFF and we do electron beam patterning of platinum, essentially, to create electrodes on the top of our sample. So here you saw this image with Peggy's talk in the first session of today. She talked about the fabrication. I'll talk more about what this actually allows us to show in our devices. Essentially, the main thing to know here is we have a very large top electrode of platinum here, and then around the edge, we have these small electrodes that we use to create our device. So if we have a zoom in here, we can see that we have platinum. This is the edge of the top electrode. This is our small electrode. And this region here essentially constitutes our device area. So this is a scanning probe microscopy image where we can see the topography of our sample. And I'll show you later how we use different scanning probe microscopy techniques to actually probe not only the ferroelectric domain structure, but also the electronic properties of our devices. Before I move on, this is also the size of this device is of the order of several hundreds of nanometers. So we're talking about nanoscale devices at the moment. Okay, so how do we do this experiment? Essentially, what we have to do in our experiment is we have to correlate the domain structure, where the domain walls are, with the electronic properties of our device. We have to prove essentially that if we have domain walls, we will get a different device behavior than if we don't have domain walls. And so to do this, we look at a region of our devices in this boxed area here. We electrically ground our large platinum electrode, and we use our AFM tip to scan this region, and we're going to image the domain walls. We're also going to look at the conductivity of the sample. The other purpose of this AFM tip is to actually allow us to conduct, to connect to this small electrode, thus completing the circuit and then measuring the electrical properties of our sample. Now we had a nice introduction, I think, on PFM earlier today, so I won't go into too much detail. I'll just refresh the audience that essentially PFM allows us to use the piezoelectric properties of ferroelectrics to determine the domain directions. So for example, between two domains, we want to see a domain wall, but we need to show what the domain directions are in the different domains. And so that's what we use PFM for. So our SPM we use is PFM, and also conductive AFM, where essentially we're just applying a small current through here to actually probe what is the resistance of this full circuit here. All right, let's have a look at what we can do with this device. So the first thing we need to do is we need to show that we can actually create domain walls as we want. So essentially we have to be able to create and erase them. So this is the as-grown domain state of our sample. So here we have the out-of-plane PFM phase and the in-plane PFM phase. Let's focus on the in-plane because that's the most important part for this device. Now, you can see that this region here is all essentially a uniform contrast, which tells us that the polarization is pointing to the left. Now, we then put our AFM tip on the small electrode here, and we apply a pulse of 8 volts for 1 second. What happens is through the electric field that is applied between this electrode and the large electrode, we actually nucleate a domain that has a different domain direction. You can see from the different color of the contrast over here. And you can see there are domain walls that actually connect the small electrode to the large electrode. So essentially what we can do is we can create these domain wall pairs at will. We can actually reverse that bias and actually remove those domain walls as we wish. And so we can essentially turn on and off the domain wall situation in this device. And this is non-volatile. These domain walls remain there for several hours. The next thing to do is to correlate what is happening with the domain structure with the electronic properties, the electrical properties of the device. So for that, we use PFM in conjunction with CAFM. This is the conductive AFM technique. And let's start with the domain wall free state, which we see here. So this is a constant contrast in our polarization map. And the CAFM shows no features, essentially. We see a large value of current here because we're actually probing the grounded electrode. So we see some current flowing. When we look at the domain wall present state, so here now we have the reversed domain with some domain walls connecting the electrodes, we see in our current map, we see some hotspots, first of all, for the actual domain walls themselves. This makes sense because they're conductive, but we also see a high level of conductivity at the actual electrode itself. Now, if we actually look at the amount of current that's flowing, and we compare the off state with the on state by taking profiles along these lines across the small electrode here, we see an on-off ratio of around 1000. So this is 10 to the 3, not too bad for a prototype device. So here what we've actually shown is unambiguously that the domain structure in our device actually dictates the electrical behavior. And so this is exactly what we want to be able to show, a memory that has a 0 and a 1 state. It's essentially a binary memory. This works very well with a number of different devices. So this is not just a single device. We have pretty good lithography techniques such that we have this repeatable for several different devices. You can see the ratio is close to 10 to the 3 for all of these devices. So we have a nice prototype with reproducibility in different devices. The next thing to check for a memory is, of course, how long will the states be stable, and then how many times can we switch them back and forth. So the stability of the states, we have up to about 10 to the 4 seconds, which we think is actually limited not by the actual memory itself, but more about the way the AFM tip and we can actually switch these back and forth close to 1,000 times. Of course, these are not going to be great for a commercial memory straight away, but we think for a prototype, these numbers are quite good. So that's the end of my talk. Basically, I've shown you that we've made a prototype of a ferroelectric domain wall memory. This is only available to us because we have accessible to us really good fabrication and of course the state-of-the-art lithography at ANFF. And then we have our scanning probe microscopy techniques that we're experts in as well. The next thing we want to do is we want to move forward with improving the retention of these devices using something we've pioneered in our lab called designer defects, which is essentially in the fabrication stage, putting some defects in and then actually making sure that these domain walls don't move. And then essentially making the retention up to several years instead of just several hours. So thank you so much for your attention, and I'd love to take some questions.
Thank you very much. And there is a question from Wendy. Did you calculate the sub-threshold swing of this switching device?
Oh, that's a good question. I don't think we did. That was not a motivation for us. I think the key issue here is that I think we need 8 volts. That's our kind of threshold, if you like, at least for operation here. And you can also see here the 1 second time frame. Of course, it's not a fast device, so we have to, this is something that needs to be optimized in future, materials development.
Got it.
Can this technique be used for profiling the NP junction, cross-section of NP junction?
Interesting. What is? I'm not sure of the resolution. So, what is the typical length scale for that one? I'm not actually familiar.
We would like to scan like 10 by 10 microns.
Oh yeah, it should be fine. So the key thing is fabrication of the sample. If you want to make a cross section, you'll need to actually create it, and then.
This is another story. But if that sample is done somehow, I was just curious if this technique will pick up the N and P sides.
I think so. Yeah, I think that should be possible. So let me make a comment. I feel that this technique has been used for the LAO STO 2-dimensional electron gas that some of you may be aware of, and this one can very clearly see the conduction kind of layer, if you like, in that system, and that's done using cross-sectional methods. Yep.
All right. Thanks.